with the presentation? Okay, cool. Thank you. Thank you for joining my session today. My name is Dinesh Joshi, and I will be talking about building Apache Cassandra behind the scenes. This is Cassandra 4.0, and a little bit about me before we get started. I work at Apple, and I work on Cassandra. I'm also an Apache Cassandra committer, been in the community for a while, and my major current work in Cassandra is related to Cassandra 4.0, although we've made certain bug fixes to 3.0 as well. But 4.0 is where I have contributed my maximum time. So with that, let's get started. So I'm going to talk about some of the industry trends first. We're going to talk a little bit about the history of Cassandra and also the architecture. We're going to talk about Cassandra's internals a little bit, and then talk about challenges in testing and validations, and finally testing Cassandra and what makes it very hard, and a summary. So For those of you who are not familiar, 4.0 is one of the first releases that has been in the works for over 2 years now. I want to add a little bit of context as to how 4.0 is being built and what are the things that we are doing to ensure that this is a good, stable release and as bug-free as possible in the Cassandra community. So can anybody guess what this chart represents? And you can type it in the chat what your theory is about this chart. And I'm sure everybody is going to relate to this particular chart once I tell you what it is. Any guesses? Okay, I'll just put a label on it. This is the industry data growth trend. Basically, the industry which I'm talking about is everybody that today is attending ApacheCon is working in. Basically, the industry has experienced a lot of data growth over time. And with COVID-19, it's gotten even worse because everybody's working from home. There's a lot more emphasis on remote working. And so the data growth in the industry is phenomenal. And with this data growth, the systems that store the data have also they need to scale as well. And there is an added emphasis on the quality of the storage systems as well as the speed and reliability of the storage systems. So that's what our industry is experiencing at the moment. And so Cassandra is not immune to any of these industry trends as well. And so with that said, let's see what Cassandra looks like in the community. So currently, Cassandra has various releases that people use in production. We have Cassandra 2.x series, which is stable and widely adopted. And then there is the Cassandra 3.0 series, which is also stable and adopted in the industry. And we have Cassandra 3.11, which is also stable. It has some performance improvements over 3.0, and it's also quite widely adopted. So we have various releases of Cassandra with some incremental benefits in the community. And 4.0 is the next unreleased version of Cassandra that we are working on, as in the Cassandra community is working on. And this is the next release of Cassandra. And this particular release of Cassandra is quite important because it's been in the works for quite a long time, and also it brings in a lot of features to the table. So these are, if you look at Cassandra changelog, you're going to see pages and pages of changes. And if you try to look at all the changes, you will find that there are over 400 changes in Cassandra 4.0. And these changes are quite significant. So in the community, whenever we make a commit, a change is termed as a could be a feature, or it could be a bug fix, or it could be a minor change. But with Cassandra 4.0, we have a lot of changes that are coming in, and with those changes comes the risk of bugs and regressions and stuff like that. So let's see what Cassandra's internals look like, because with all of these changes, we need to test Cassandra so that we ensure that the release is reasonably stable. So here's the Cassandra architecture. And most of you should be familiar with this architecture, but if you're not, I'll just take you through it. So with Cassandra, we have individual nodes that are participating in the overall ring, which is called the Cassandra ring. And this makes the Cassandra system as a whole act like a distributed hash table, because each node in the ring is going to have a certain range of data. And that range of data is called the token range. And this node is primarily responsible for storing that data, but also we need to make sure that this data is available for consumption without any downtime in case a node goes down, right? So this node is going to take the data and it's going to replicate to all the replicas of that node. And typically in Cassandra, we have a replication factor of 3, which means that the data is going to be stored across 3 different replicas for durability and availability. With that said, whenever a node fails in Cassandra, the from the customer's perspective, from the client's perspective, the system continues to function as a whole, but we have to internally repair that node and ensure that data that that node has is consistent. So apart from the overall architecture of Cassandra, Cassandra has various components within each node. These components are non-exhaustive, but these are the most important components, which is the storage engine, the coordination layer. There are activities that it runs, like repair, which is to reconcile data differences between nodes in the cluster. There's streaming, which does data transfer between nodes in a cluster, and compaction that ensures that data that is deleted or is no longer reachable is dropped over time. So, and then there is also the inter-node communication in Cassandra, which means all the nodes, they need to participate in a cluster, and in order to participate in the cluster, there is inter-node communication. And there are other parts of Cassandra that I've not really called out here, but there is gossip and other parts of Cassandra that participate in making the cluster look like a single entity from a client's perspective. So with this said, there is a lot of stuff in Cassandra that is participating in making the system, the whole database work as a single unit. And so whenever we change anything in Cassandra, there are changes that may affect all of these layers or some of these layers within the database. And so when we change something, we need to make sure that there are no regressions that are introduced and that the system continues to function as previously expected. And as we dive into the further slides, I'll talk about the progressive difficulty of testing these different parts of Cassandra. So, so let's talk about testing Cassandra now. There are various challenges in testing Cassandra, and those challenges are primarily because there are a lot of variables. So anybody who has operated Cassandra knows that there are a lot of components within Cassandra, and there are a lot of knobs that we can tune. So for example, we can change a lot of settings. And these settings can lead to great performance for certain types of schemas. And some of these settings may introduce performance regressions for other types of schemas. And so there are certain behavior characteristics that are dependent on the settings that Cassandra has. So and to add to this, we have a different deployment configuration. So you can deploy this in 2 data centers, 3 data centers, 4 data centers, 5 data centers. You can deploy them in large EC2 machines, or you can deploy them in very tiny hardware. So the deployment configuration also matters when it comes to testing Cassandra. And the schemas or use cases that you can model on Cassandra are very varied. So there's a lot of variance on the schemas that you can use, and people use Cassandra in very different ways. So now I think you get the idea that there are a lot of variables that come into picture when it comes to deploying and running Cassandra. And so naturally, when it comes to making a change in Cassandra's code base, it also means that you have to, make sure that all of these things, that the system as a whole works under different settings, different components behave exactly the way they were supposed to behave earlier, and that we are not regressing, we are not losing any data, we are not causing any sort of bugs from the usage standpoint. Um, so what does testing in Cassandra look like right now? So in the open source community, we have various unit tests. Cassandra has a lot of unit tests. It has Python D tests and upgrade tests and in-JVM D tests. And D tests are basically distributed tests. What that means is we spawn various instances of Cassandra, and each instance is a physically separate process. In case of Python, whereas in JVM D tests, we have a single JVM that kind of models different instances of Cassandra as threads within the same JVM. But the general idea is that you can launch a 3-node cluster or 5-node cluster, and you can run some tests within the scope of your test machine. So, let's say you have a laptop and you can launch the Python D tests and it runs the D tests. But these D tests also require a lot of resources. So, but they can be still run locally on your machine. In-JVM tests are used to test some of the components, and these are more focused for doing white box testing in Cassandra. So what that means is you have D tests that are running within the JVM, but it is a single JVM, so you can much more easily mock out components, especially the networking component in Cassandra, to test Cassandra's code flow. And this also makes it easier for a developer to debug failures that are pertaining to a distributed setup of the cluster. And upgrade tests are also part of the test suite that Cassandra has. And the upgrade tests basically test that when Cassandra is in a upgrade state, or we are upgrading Cassandra, and it is running in a mixed mode state, that we don't regress. We don't regress from the existing state. So what that means is, let's say there's a cluster that you have running 3.0, and you are upgrading it to 4.0. And an upgrade test will check when the cluster is partially in 4.0 and 3.0, that there are no regressions, because one of the underpinning principles with Cassandra is that we never take the database offline. Even in case of upgrades, we continue to function. And so as we update individual nodes, the customer doesn't experience any downtime, which is not something that other databases can typically do. So with all these tests, the natural question is, are these enough? Are these tests enough? And the answer to that question is a resounding no. And the reason why these are insufficient is because here's a graph. Um, the source of the graph is below, and we have a lot of issues that we've seen being patched in Cassandra post the 3.0 release. And some of these are availability issues, some of these are crashes that the user experiences, which is the SRE's experience, and then there are correctness issues as well. And these defects are non-trivial to fix, and you may not always experience these failures, or you may not always hit these bugs. And it's only when you reach maybe a certain scale, or you are using Cassandra in a certain configuration, that you may actually experience these issues. And so obviously the logic follows is that if we see these errors or defects in Cassandra, then there are then we need to figure out a better testing strategy, more effective testing strategy to ferret out these bugs. And so going back to the challenges that we have, if we look at why it is hard to expose these bugs, is because there are a lot of moving parts. The components that make up Cassandra, the settings, the deployment configuration, the schemas, the use cases, and in many situations, we have to use Cassandra in a mixed mode. That is, during upgrades, we are going to see a lot of these issues crop up. It's only when you set these components in a specific configuration that you might actually experience these issues. So what makes this even worse is the in a distributed system, time is a quantity that is kind of weird. What I mean to say is that in a cluster, when you have different nodes talking to each other, each node has its own clock. And it's a well-known phenomena in a distributed system that when you're coordinating between two nodes or two processes that have their own clock, it is very hard to actually establish a happens before relationship, which means that if the clocks drift in the systems, it's going to affect the way the same query or same set of packets that are flowing between the two nodes to be processed in a slightly different way, depending on how the timing is. The other issue with timing is that it's very hard to simulate certain race condition. A lot of race conditions are due to timing issues in the system. So if, let's say, you hit a error condition or a bug because there is a slight variability in the way packets are being delivered in our system, then it is very hard to do to simulate that particular situation exactly in a test scenario. And especially this gets worse because when you have, let's say, a 10 node cluster or a 20 node cluster, now there are messages being sent back and forth across a lot of nodes. So eventually what happens is that if you have to simulate this entire system, it is a very complicated problem, and timing is an issue here. The other issue is the message delivery in Cassandra 4.0 is asynchronous. Well, what that means is we have switched to async IO. So some of the operations that were obviously synchronous are asynchronous at this point. And as a result, there are a lot of edge cases where earlier a synchronous code flow is now asynchronous, and that also introduces a difficulty in testing. Node failures is another big issue that if you want to simulate a node failure, it's generally much easier to simulate a node failure than compared to the first two issues. and also race conditions within the process as well as across different processes of Cassandra that are running in different nodes. These race conditions are very hard to simulate. So any piece of code that is multi-threaded is by definition it is non-deterministic and it is harder to test. So if you go looking for a library in Java that allows you to test concurrent code, you would be hard pressed to find something that is reasonable. And finally, network flakiness. So believe it or not, there are a lot of edge conditions that are exposed because network drops a packet or there is flakiness in the networking, and or there are system parameters that are set differently in Cassandra. Uh, uh, what I mean to say is the system that is running Cassandra has a lot of parameters that make network behave in a different way. So the test setup for that network networking is going to also change the way networking works within Cassandra. And finally, Java's garbage collector. This also adds a form of a non-determinism in the Cassandra process. So that all of these challenges are in addition to having a complicated code base as well as a ton of distributed components that are talking to each other. So coming to testing Cassandra 4.0. So how do we test Cassandra 4.0? There are various approaches that the community has adopted. Uh, One of the approach is replay testing, and we'll dive more deeper into each of these test scenario testing approaches in the further slides. But the first one of the first approaches is replay testing. The second approach is fuzz and property-based testing, and third approach is distributed tests and fault injection testing. And the last approach is upgrade testing. And let me talk through these individual testing strategies. So replay testing is basically where we capture traffic and we replay it. And in 4.0, we have this feature called as FQL, which is full query logging. And with this feature, what we can do is we can capture logs or rather capture queries and log them into binary files that are stored on disk, and then take those files and replay the contents of those files. So the queries that you actually experience in production, we can take those queries and we can capture them and on individual nodes or all nodes in a cluster, and then we can take those individual queries and replay them on a test cluster. And this is a very effective way of testing Cassandra. Um, so in this approach, we can either capture all queries or we can also sample queries in individual nodes. And this is a high throughput approach for testing Cassandra. What I mean to say is that when we capture queries in production, it doesn't have to compromise on how many queries we capture. The implementation that FQL has is a very low overhead implementation. So as long as you have enough disk I/O, we can capture every single query that is making it to that node and then log it without really having to drop the number of drop a few queries on the floor because it may degrade performance. And replay testing is typically carried out on a cluster that is upgraded or is in the process of being upgraded. And that basically simulates a scenario where you have upgraded Cassandra with the same data set and you're throwing the same queries at that cluster. And the expectation is that that cluster also gives you the same data and responses that your old cluster gives. So from a user standpoint, when we upgrade a user from, let's say, 3.0 to 4.0, functionally they should not see any difference in the response characteristics, meaning the latency and the throughput of queries, and also they should not see any changes in the read or write path of Cassandra. So the results of the queries pre 4.0 upgrade and post 4.0 upgrade should be exactly the same. So and in all dimensions. Coming to fuzz and property-based testing, um, Cassandra recently open sourced this tool called Harry. And Harry allows you to perform basically fuzz testing. And so before we talk about this further, let's talk a little bit about fuzz testing and property-based testing. So these are testing tools that have been around for quite a long time. Um, the basic idea of these tools is to explore the state space of a component. So let's say you have a component that takes a certain set of inputs, and you can pass various valid values in those inputs, and you get a valid response back. But what happens in the real world is that that component may not always get a valid input, in which case there are edge cases that are left unexplored. And what fuzz and property-based testing does is helps you establish an invariant for that component and explore the state space of the inputs for that component. And the tool allows you to pass in various values and ensuring that the invariant that you have established is always true. And this approach has allowed us to expose issues um, in um, in areas like checksumming or framing within Cassandra's internode networking protocol. Um, and so this is a very useful tool where a developer may not be able to write a very effective test or explore the state space in its entirety. And these tools allow us to do this very easily. Harry is a more recent contribution into Cassandra, but prior to Harry, we use a library called Quick Theories, and it is able to do this first testing or property-based testing in Cassandra's code base. And we have a more in-depth article about this on the Cassandra blog. If you're interested, you can go to the blog link and basically look at how Cassandra is using property-based testing and fuzz testing. The other approaches are distributed testing and fault injection testing. In this case, what we do is basically spin up a cluster and run tests against that cluster. These tests, while these tests are running, we inject fault, which means we use stuff like Chaos Monkey or Chaos Gorilla, and we can introduce chaos in the overall system. This allows the system to survive failures, and at the same time, we are able to expose bugs related to edge conditions, like when hardware fails, or when a node suddenly goes offline, or there's flakiness when the node comes online, goes offline repeatedly. And this is one of the more effective ways of ferreting issues out in any distributed system. The final testing strategy is upgrade testing. This is one of the most critical, in my view, to test the upgrade scenarios in Cassandra. And this is not really a special type of testing, but this is basically forcing the cluster into a situation where it's running in mixed mode and making sure that all the components are behaving the way they're expected to behave. And so the testing strategy that we apply here is no different from the previous testing strategies. But what is different here is that the cluster is actually running in a mixed mode situation. And so there are what this allows us to verify is that the cluster is going to behave exactly the same as a 4.0 or a 3.0 cluster if it is running in a mixed mode 3.0 and 4.0 cluster. Obviously, you won't expect all the features to work as in the case of the client. You would expect all the features to exactly work, but the 4.0 specific features would not be um, uh, available because the cluster is running in a mixed mode scenario. And once the cluster is fully upgraded, you would expect that the cluster would expose functionality that is 4.0 specific, and it's available to the customers to use it. So, so with that said, I'll summarize. 4.0 should be stable. That is the goal of the Cassandra community. And a lot has gone into ensuring 4.0 is stable. A lot of issues have been already reported and fixed. There are a few issues that existing techniques miss. They do catch some of the very obvious failures, but there are certain issues that they have missed. And so the community is working really hard to ensure that all of these issues are exposed before we declare 4.0 is stable. And the final takeaway is testing any distributed system is hard. The testing a stateful distributed system like Cassandra is even harder. And the emphasis that we've placed on testing is pretty phenomenal. And we can't do it by ourselves. So please help test Cassandra 4.0. The beta 2 for Cassandra is already out on our website, and you can just download, install it, and try it out for your use case. Maybe you'll find an issue, maybe you'll not find an issue, but at least we will get some great feedback from our users. So that is, I think that is very critical for us at this point, as we are all trying to get 4.0 out soon. And finally, we are hiring at Apple. So if you're interested in working at Apple, we have a ton of positions open in our organization. Please follow the link on the screen, and it should hopefully take you to the jobs page at Apple where you can apply. This is a ApacheCon specific link, so please do apply if you're interested in working at Apple and solving some of these problems. All right, that's it from me. Thank you very much. Apologies for the delay in joining the session, and I'm open for any questions if anybody has any. You can type the questions in the chat. All right. Sorry. So I didn't see the previous questions in the chat. All right. So the graph was not number of bugs over time. It was distribution of bugs. So these are overall bugs, and they're classified by defect type. And so the overall bugs that were caught so far post 3.0 release are summarized here. There's a Jira link. If you go to that filter, you should see all the individual issues. Most of these issues won't be something that you would be able to. Uh, yeah, I mean, most of these issues are not something that you would encounter under normal circumstances. These are really, really weird issues. Um, yes, about 4.0 stability. Um, I don't know. We are testing. There is a very interesting discussion that happened earlier on the dev list about the overall freeze that we had in order to focus on stability. Obviously, there are different viewpoints that people have about stability. Sorry, I'm going back and forth. I think there are a lot of issues that were found and fixed in 4.0. We're still finding issues, and the community is working really hard to um, make sure that we are able to fix those issues. Example of issues that existing techniques miss. Uh, so. Um, uh, there are various examples. I think if you see this filter, you will see all of these. What immediately comes to my mind is a couple issues with related to networking, and networking is one of the most annoying pieces of the overall distributed system, right? Netflix actually encountered this issue with stateful firewalls on AWS, which caused us to um, add a feature slash a configuration item which allows you to tune TCP user timeout. I don't know how many of you have heard of TCP user timeout as a kernel parameter slash TCP option. It basically deals with unacknowledged TCP segments, and what happened is they encountered an issue where AWS was keeping TCP connections half open. And when a TCP connection is half open, what that means is that either the sender, I think either on the sender or receiver side, the connection remains open, but there's nothing on the other side. And this actually causes a lot of backlog of network packets, and that is an issue um, for folks because well, the whole system re- depends on networking, and if networking stops functioning, you run into this issue. So I don't know the Jira off the top of my head, but 4.0 allows you to tune this parameter so that you don't have to deal with TCP half open issues. Now, this is something that I don't think any of the existing techniques could catch unless you can very accurately um, simulate the network. But even then, I'm not very optimistic. So this is only something that you can encounter when you actually deploy it to a real live environment and try testing Cassandra. So that's an example. Any other questions that I could answer? I think we are a little bit over time. How do you test different consistency levels in Cassandra? I uh, Again, there are various tests for testing different consistency levels, but that this is where I think we need more diversity in testing, which means if you're using Cassandra in a very different way with different consistency levels, then you would want to put this on an actual cluster and try it out and test it. There are a lot of tests which test different consistency levels work as expected, but there's no substitute for actually putting this on a set of machines and running your application against that cluster and ensuring that it works. in with the consistency levels that you require. So that's why I encourage try testing it by yourself with your application. I know there are people who use very weird consistency levels, and we may not actually capture this in a test, but you may actually encounter this issue. And Edward, I agree. 4.0 is comprehensively tested so far. All right, so we are a few minutes over. If there is any question that you have, you can ping me on Slack, Apache Slack, um, and I'll be happy to answer your questions. All right, so thank you everybody for joining this session, and hope ApacheCon is great for all of you.